So in last lecture, we have seen direct loading test and OCSC test. So in case of direct loading test, you know that we're directly applying the load on the alternator. So the step-by-step procedure is we have to connect field, the field rheostat, let us say suppose RF, it is kept at high value, okay, initially to maintain the field excitation at 0. Then we will start the prime motor. It may be induction motor, DC motor, right? In our case, it is an induction motor, three-phase induction motor. So by using auto transformer starter, we can start this three-phase induction motor. So it will rotate the field winding. And once prime mover is started and field winding is started rotating, at that time we are going to apply the field excitation. It may be 220 volt DC or 230 volt DC, but normally it is 220 volt DC. Okay, as I told you that we have kept this resistance at higher value. The excitation is initially very much, means it is zero. Okay, it is zero, and load is not connected to the alternator, armature of the alternator. Now gradually we are going to increase the field excitation by decreasing the resistance. So we'll increase the field excitation in such a way that I will get rated voltage at the terminal. Okay, this VL should be a rated value. Once I got the rated voltage and I have maintained some field excitation as well as the rated speed. Let us say suppose it is a 1500 RPM. So I will say that there is a voltage of 415 volt. Okay, once rated voltages appear across these two terminal, I will connect the load. But initially, all the load is switched off. So I have connected the load and gradually I'm going to increase the load. And one by one, I have to mention the or note down the reading. So which are the reading I have to take? I will mention observation number, load current and rated voltage. Provided this field current and speed, it should be constant. So what I will do, I will just take next reading, second reading. By increasing some load, what will happen? Load current will increase and the voltage will be some, it is having some value. Let us say suppose by increasing the load, what will happen? There may be a drop in a voltage. So we have to adjust the excitation to maintain the rated voltage. So once I got the rated voltage at full load, means there is a full load current. Okay. In our case, let us suppose it is a 4.5 and I got the value of rated voltage. It is a line to line 415. I'm going to remove the load directly and I will note down the open circuit voltage. And once we got these two value, I can measure the voltage regulation as EPH minus VT upon VT into 100. Make sure that these all the values are per phase value. As we are measuring here line values, but we have to calculate the phase voltage by VL upon root 3. That VPH is equal to VL upon root 3. So by using this formula, we can calculate the phase voltage and the regulation that can be calculated by VPH minus VT upon VT into 100. Now, so this is all about direct loading test and its observations. We'll see in detail in the practical how to perform this direct loading test. Then come towards the indirect loading test. So indirect loading, in case of indirect loading test, there are different methods to calculate the voltage regulation. First one is a synchronous impedance method. Second one is, can anyone please tell me? Okay, so we started with the first method, but before that, for these all three methods, we require some primary data, and that primary data is nothing but the, I need to know what is the value of RA. RA is nothing but the armature resistance. So how to measure the armature resistance? In this case, we are going to apply, see that armature is disconnected, means we are not starting or not giving any supply to field, or we are not going to rotate the prime mover. Just remove the armature from whatever load it is connected, it is connected to any load, and in that case I will apply some DC voltage. It may have some value. Okay, we have to apply the DC voltage by which there is some current through the winding. So this winding is kept open and in the terminal R and Y, I have applied some DC voltage and I'm going to measure the DC current over there. Fine. So I will get VDC and IDC. Okay. You know that R is equal to V upon I. So by using that formula, I can measure the resistance in between RY, YB and BR. So that resistance will be RRY is equal to VDC upon IDC 1. Then RYB is equal to VDC 2 upon IDC 2. And RBR is equal to VDC 3 upon IDC 3. Once I got these three values, I can measure the or calculate the RDC by using this formula. Now, what is RA? RA is nothing but the AC resistance, okay? And this is present due to the, yes, due to the skin effect, the value of RA and RDC is different, okay? If there is no skin effect, in that case it might be same, but due to skin effect, what is happening? The effective resistance is increases. So what is the value of that effective resistance in case of AC supply? RA is equal to 1.25 to 1.5 times RDC. Means our AC resistance is 1. Let us say 1.5 times DC resistance. So in this way we have calculated the RA. Next step, I have to perform the open circuit test. So in case of open circuit test, the same way, we have to keep this resistance at high value to maintain field excitation at 0. We will start prime mover and rotate it to rated speed. Armature is means no load is connected. That means it is kept open circuited. So by increasing this field excitation gradually, I will measure the open circuit voltage. I will note down the reading. Okay. So up to what reading we have to take? We will take the reading of VOC up to 25 to 50% of the rated voltage. Okay. So once I got this reading, I can plot the graph was that VOC versus IF, and the nature of this graph is like this. Okay. And it is not, it is also called as a, yes, magnetizing curve. Fine. So at I of 1, I will get the rated voltage, and at I of 2, I will get the open circuit voltage, which is nothing but the E0. So this is open circuit test. After that, we have seen a short circuit test. So in case of short circuit, I did what? I just short circuited all these terminal. See, in this case, the taken must be or the care must be taken that we have to keep the excitation 0 at every case or at the time of starting. So again, started this alternator or prime mover is started, and then field will start rotating again as it is short circuited, and accidentally or some due to some reason, if I'm going to apply excitation at the time of starting, there might be a very high current flowing through this link, and it may cause the damage of the alternator or armature. So as I told you, I have kept this resistance at higher value, so the excitation is 0. Once prime mover is started, I will just gradually increase the excitation, this field excitation, and accordingly I will note down the short circuit current reading. Okay, so I will increase this IF in such a way that I will get the rated current in this ammeter. So once I got the reading, means once I got the I rated, I will stop the reading. Stop taking the reading. Okay. So let us say suppose there are near about 4 to 5 readings, and if I'm going to plot the graph of ISC versus IF, I will get a straight line. Okay. So this is nothing but the short circuit test. Is there any doubt? Synchronous impedance method. Okay, so in this lecture we are going to see the synchronous impedance method or EMF method. So why it is called as a synchronous EMF method, and what to do with that synchronous impedance, that we will see. It is, if you feel something is important, you can note it down. In this method, we have to find the synchronous impedance by using that open circuit test and short circuit test to calculate the voltage regulation. Okay, so we are using synchronous impedance to calculate the voltage regulation. So it is called as a synchronous impedance method. Okay, so in this method, the effect of leakage flux and armature reaction as a voltage drop we are considering. Okay, in this method, You know what is leakage flux? Yes or no? Yes. Do you know or not?
Yes.
Okay. So the effect of this leakage flux and armature reaction as a voltage drop is considered. Fine. Keep in mind. Okay. So the substitution of this voltage for the flux is nothing but the reason that it is called as a synchronous impedance method. Means, see, what I told you that, well, instead of flux, we are keeping or representing that flux as a voltage drop. So it is called as a EMF method. Okay. So the substitution of voltage. Such type of questions may be asked in your oral examination. So the substitution of voltage for flux is the reason that synchronous impedance method is called. I hope this is clear to everyone. Okay, so again, as I told you, by using synchronous impedance, it is calculated by using open circuit test and short circuit test. But there is one disadvantages. Instead of disadvantages, what is happening? Whenever we are calculating synchronous impedance by OCC and SCC test, whatever will be the impedance or the regulation we are going to calculate, it is very much larger than the normal load calculation. Means regulation with synchronous impedance is very much larger than actual calculation. So in case of synchronous impedance method, whatever the regulation we are getting with synchronous impedance method, it is having higher value than the calculation, actual calculation. See the procedure to calculate the voltage regulation by using synchronous impedance method. You can note it down. Procedure using synchronous impedance method. So for this method, what is the data which is required for us? Yes, to calculate the synchronous impedance method, which data is required? Armature resistance and open circuit characteristics and short circuit test characteristic. The first step, we have to calculate synchronous impedance. Calculation of synchronous impedance. And to calculate the synchronous impedance, first we have to plot the open circuit test and short circuit test. Okay, any doubt? So plot open circuit test and short circuit on same graph. Okay, so what we have to do, see, suppose this is a graph paper in which this is IF, and I'm going to plot OCC and SCC. Okay, so I will consider here is a ISC, and on the same axis I will consider here as a VOC. Okay, so how to plot means, if I'm going to plot that open circuit test, it will be like this. Okay, and again, if I'm going to plot short circuit test, it will be like this, right? Now what we have to do, once this graph is plotted on the, or this it is OCC and ACC is plotted on graph paper, on the same graph paper, we have to calculate the field current required for produce uh, full load current. Okay, so let us say, suppose this is a I of SC, at which I'm getting the I rated. Okay, and at the same reading I have to take the this VOC. So what is ZS? This ZS is nothing but open circuit voltage or EMF. Open circuit EMF per phase. It should be per phase value divided by short circuit armature current. But the condition is for same field current. Any doubt? You can note it down.
Yes, sir.
Calculate the synchronous impedance. We have to plot OCC and ACC, and once it is plotted for the same field current at which we are getting the rated current, you have to plot what? You have to consider that VOC and ISC. So ZS is equal to open circuit EMF upon short circuit armature current for the same field current. Note down, please. See, every time we need not to plot these characteristics. Means sometimes in problem they have mentioned that the VOC and ISC for same field current. Let us say suppose VOC and ISC for IF, same IF. If it is given, so we need not to plot this characteristic. So let us say, suppose I just got the values of ZS, that is nothing but the synchronous impedance by using this formula. It may be by using this graph, or let us say, suppose we have given the some values directly in the numerical. Now, next step, let us say, suppose second number step, I got the value of ZS. Can you tell me what is ZS? ZS in terms of RA and XS. ZS is equal to RA plus JXS. So if I want to calculate the magnitude, ZS square is equal to RA square plus XS square. Am I right? Okay. So in this case, this RA is known. It is calculated by using that test. Okay. Then ZS is known. By using synchronous impedance method, we have calculated ZS. So how to calculate XS? So XS will be under root ZS square minus RS square. Got it? Okay. Next task. Once I got the value of XS and ZS, I have to calculate the voltage regulation. But how to calculate that voltage regulation? See, if we consider, let us say, suppose I'm going to draw the per phase circuit. This is applied voltage. This is RA, and this one is, let us say, suppose XS. Sorry, XS. RA plus XS, and there is a EPH. Is it covered or is it alone? Or we can say it is a EPH.
Yes, sir.
Can you write down the formula for EO? What is the voltage EPH? Let us suppose this is VA or VPH. So if I'm going to use this equivalent circuit and plot the phasor diagram, I will get the formula. See, that is not a part, means it is not expected that you should write down the phasor diagram, but I'm just telling you. Let us say suppose this is terminal voltage. I'm getting some voltage across this terminal voltage, so that VT is equal to this voltage minus. So if I'm going to use that formula, we'll get the formula for voltage regulation. See, right, values of RA and XS is known. XS are known. Value of no load EMF per phase. EMF per phase can be calculated as this EPH is equal to. So right now we have considered a lagging power factor. That's why this formula is coming as a VT cos of phi plus IRA whole square plus VT sine phi plus IAXS whole square, and this is for lagging load. We got the value of EPH. Let us suppose for lagging power factor, this is like this. EPH is equal to VT cos of phi plus IRA whole square plus VT sine phi minus IAXS. See, if there is a leading power factor or leading power factor, lagging this sign is positive, for leading this sign is negative, and if there is a unity power factor, this EPH will be, see, unity means what? Phi is equal to 90 degree, so cos 90 is 1, sin 90 is 0, so this term will become 0 only. So for unity power factor it will be VT plus IARA whole square plus IAXS square. This is for unity power factor. And once I got the value of this EPH, the voltage regulation can be calculated as the fourth step, voltage regulation. It is given by the percentage voltage regulation. It is equal to this EPH minus VT divided by VT into 100. So this is the formula to calculate the voltage regulation by using synchronous impedance method. So I hope this one is clear. I will just revise this thing in next lecture, and again, as I told you, I will tell you how to derive this formula.